Hello. In this video, I'm going to be covering the basic ideas when approaching determinate torsional loading problems. Okay, so steps in the analysis. First thing you're going to do is look at the shaft and then break it down into segments. Segments are basically, segments of uniform geometry and load. Boundaries occur whenever a load changes, diameter changes, material changes, or the composition changes. So really any changes at all, and you're looking at having a different segment. Then what you do is you look at each of these segments one at a time. Usually for simplicity, you keep it all the same. So I like to work from the right towards the left. You look at the shaft from the side and just start on the right end. And then that's basically it. Overall, this process is very similar to axial loading if you've already done that. Now, these problems we're going to be doing, at least for now, are determinate problems where you have one end clamped and then the other end is free. So we have the left end clamped, right end free, starting from the free end, working towards the left end. If the ends were both clamped, or say it undergoes an amount of twist and then it becomes clamped, then that's an indeterminate problem which require additional calculation. I'll be covering indeterminate problems in some later videos, but for right now we're just working with determinate problems. So in this slide we've got an example of a shaft, a fairly complex shaft, but really it's just here to show you how you break things down into segments. So if you look at the right end here, we've got a 200 inch-pound torque applied in the clockwise direction around it. And you can see that for at least length 1, it just stays a uniform diameter. And then here at this boundary, there's a new torque added and there's a change in diameter, making a new segment. After that, the material changes, new segment, then it changes composition and diameter, and so on. You can see here that for 5 and 6, it's same material and geometry really, but in the middle of it, there's a new load added, which means then, breaking it into two different segments, and so on. It's pretty intuitive. One thing to note is that twists counterclockwise, clockwise, it's when you're there, it's around the central axis, and they're rotating. When you look at it from a cross-sectional view, that's where it's clockwise, counterclockwise, and so on. The shaft itself is going to want to twist in the same direction of the torque. So moving on to equations, kind of the most basic shafts you have are, the most basic is solid, and then you can also have hollow shafts. There's the polar moment of area, whereas with axial loading, you're just concerned with the cross-sectional area. Well, this is somewhat similar. It's the polar moment of area. And for a solid shaft, it's pi d to the 4th over 32. For a hollow shaft, you're just worried about the material in the outer part and not about that hole. You just worried about the material part. So that means you have to subtract the inner diameter, of which is hollow, from the outer diameter. Other variables we have, there's torque, which is T, the shear modulus G, which is it's part of the material. It's a property of the material. There's the length L, that's just the length of the shaft. The maximum shear stress in the segment, you're going to have tau, which is the torque times the radius divided by the polar moment of area. The maximum shear strain, which is actually it occurs at the outer diameter, at the outer radius of the segment, it's tau divided by g. And then there's the twist angle, of which there's two different equations in there. This is the amount, this is the angle that the shaft actually twists under the load. You could have it where it's the max shear strength multiplied by the length divided by the radius, or TL over GJ. We're going to be mostly working with that TL over GJ. More complex shaft is a composite shaft, of which you have an outer and an inner material. So then you have to worry about calculations for, the outer or the inner material, or both at the same time. When it comes to the polar moment of area, you have to calculate it for both. So for the outer area, for the outer material, it's the same as the hollow. Basically, you're subtracting that area that is the other material. And then for the inner material, it's just the standard equation, and you're using your inner diameter. Of course, we have torque again, shear moduli, there's the outer and inner one, length of the shaft, and then there's the outer and inner radius. The overall torque, T, when applied to a composite shaft, is the torque itself is shared by both material, but to different amounts depending on the material. But still, in the end, they should add up to the total torque. So T outer, T inner, not necessarily equal, but they will add up to the total torque. The amount of twist, an important thing to note is that the amount of twist for either material is the same value. So even though your T outer and T inner are different, and so on with the other variables, it's all going to calculate, they have to be equal to each other. So if the only thing you're concerned about was finding the amount of twist in the shaft, you could just calculate straight up, let's say, we just go with the outer material and we can calculate the amount that twists, and that is what the shaft is twisted. But you could also then calculate the amount of twist of the inner material, and if you're getting a different value, that you've gone wrong somewhere, and then you can go and check your work. Now when you combine these two ideas, that the outer torque is a summation, the full amount of torque is a summation of the outer and inner torque values, and then the twist is going to be equal, you can derive these two equations, which let you solve for those actual values, the outer and inner torque values. Where really it's kind of like they're fractions of the full amount of torque. It's the torque multiplied by the respective shear modulus and polar moment of area divided by the summation of each of those for the outer and inner material. When finding the maximum shear stress, which, as I said earlier, occurs at the outer surfaces. So for the inner maximum shear stress, that's the outer surface of that inner material, which would be along here. And then for the outer material, it would be on the complete outside diameter. But as far as the equation goes, it's pretty much the same. It's almost entirely the same equation as finding the outer and inner torque value, but replacing the polar moment of area with the radius, the outer or inner radius, depending on which one. So that's pretty much it as far as equations go. Don't worry if this seems like a lot at first. I'm going to be making some videos of me solving some of these determinate problems to show you how it all goes down.